let's just get into the experiments that changed history. So one of the experiments that I would like to start with is the Cavendish Experiment. It's a famous one about calculating the mass of the Earth. So this is in the late 1700s. This is like 1797, 1798. This had been proposed before mid 1700s, and actually had been calculated by, I believe, it was another individual, and it was about 20% from today's value. So it wasn't terrible. So this wasn't the very first one, but this was a very powerful experiment because of what it implicitly deduced. And let me get into that. So the Cavendish Experiment, right? What is it? Well, again, determining the mass of the Earth. The apparatus is, well, it's quite simple. So Henry Cavendish, hence the name, basically made a hut in this region that was, so it was completely surrounded. It could not be affected by any air, any wind, nothing was really affecting the area inside. And in this hut was the actual apparatus. What was the apparatus? Well, it was quite simple. It was two steel balls. Again, I'm not entirely sure, but no. They were lead balls. I'm pretty sure they were lead balls. Anyways, two huge lead balls on kind of like a pivoting axis, right? But they were basically stationary. Two lead balls. Huge guys. On another axis, now when I say on an axis, I mean they are connected to each other. So just think of like a center pivoting point, and then there's two balls on either side equidistant from that point.
So you mean like an axle?
Yeah, you can think, an axle would be, but it's not exactly an axle because it's not just rods, right? It like holds the ball. Anyways, you can search up the Cavendish Experiment and you can kind of maybe see what I'm talking about. But it basically just holds two lead balls on one side, right? That's kind of like counterbalance. You can think about it. And then there are two other balls, much smaller. I'm not quite certain about the material. It doesn't really matter. But there are two smaller balls that also are connected on an axle that are basically close to one of them. So, anyways.
And both the axles are connected to the big
one? So there are four. So it's like a spoke. I don't know if I'm explaining this too well, but it's like a spoke basically, where there's one axle, two lead balls on either side, another axle, two much smaller balls on the other side, and they're all connected to this torsion string. They're basically connected on top to a string. So if you think about it, they're like kind of like rotating.
Okay. Yeah.
The steel balls are fixed. For now, the lead balls are fixed. The big guys are fixed. So the only one that can rotate is one of the axles, the axle that contains the smaller balls. Following so far? Really simple. Now, what he does is cool. It requires a little bit of time and a little bit of patience, and because you do have to put it set it up in a particular way. But if you place, and this is actually being done on like YouTube, and many people have been able to reproduce this in their garage. And if you place this axle at a certain angle, this is where it gets crazy. The gravitational force exerted by the bigger ball, well, it will move the small ball more than the small will move the big. That's obvious. So the big ball, the gravitational force it is exerting on the smaller ball, remember it's on both sides, right? So it's being attracted on both sides. So it kind of moves that axle just a little bit. You know what I mean? So basically
that much mass?
Yeah.
Just that much mass and it moves the whole thing?
The idea is to keep it at a distance where the gravitational, just hear me out. I'm talking about angles that are like 0.0001 difference, 1 degree difference, right? Okay. I'm talking about very small real changes. So what's actually happening is when the force of gravity is...
Oh, you explained this so bad. The setup.
It's two axles.
No, I thought...
It's literally two axles, and then there's a string in the center.
I thought they were connected on either side of the string.
What do you mean? No, it's like, okay, again, it's like, you can think of it like a fan. It's literally, just think about it like a fan. On one axle of the fan, there are two lead balls, huge lead balls. On another axle that's free to move, there are two steel balls. Yeah. Again, this is taking way too long for just to explain the apparatus. I'm sorry.
Keep going.
So the idea is basically there is a force of gravity being exerted between the large ball and the small ball at all times.
That's almost unbelievable.
Just listen to the experiment.
No, go ahead.
Just listen to the experiment. So what happens is there's always a force of gravity attracting the ball, right? So when you place the ball at a certain distance, the force of gravity gets large enough to actually move it a little bit. Now, this is where the interesting thing happens. The moment it moves, remember, this is a torsion, it's a string, right? So the moment it moves, there's now a little bit of a torque force that's experienced on the top. So simply because of the laws of physics, it now wants to come back to equilibrium, right? The more it gets stretched, the higher the torque. So when the torque force is equal to the gravitational force, following me so far? When the torque force is exactly equal to the gravitational force, it will come back to equilibrium. But simply because of inertia, it will continue from equilibrium, and it'll then oscillate like a harmonic oscillator.
Okay.
That's basically that is the experiment. So what does this do? What does this do? This whole time, at the torsion string on the top, there's a mirror through which Cavendish measures the change in the angle of incident light. So he positions himself in a certain place far away from this experiment as to him not affecting with it. It's like far away from it. It's basically in a abandoned completely. There's nothing else there. That's why he was so intent about this in the first place. He positioned himself in a place where incident light always kind of reflected into his big enough region. And whenever this experiment was performed, when he placed these balls, again, I'm not too certain about the exactness of what he did. I just know how the experiment works. So when he probably set this up and went to sit down, again, it's just oscillating literally forever simply because of, or not forever, drag, friction always takes it down. But the initial oscillations, the beauty of that is that the exact amount that it's oscillating, because you can calculate the torque force, right? Because remember what I said in the beginning. This torque force is exactly equal to the force of gravity that the ball is pulling it with.
Yeah.
Right. So what he's basically found is an exact equation for the force of gravity between these two masses without needing the constant G whatsoever.
That's so unbelievable.
It's crazy. But here, it's not even over. I think that was really loud. But it's not even over. This was just finding Fg without G, the gravitational constant. But his actual goal for the experiment was to find the mass of the Earth. He knows the mass of the small ball. He knows the mass of the big ball. He also knows the mass of... he doesn't know... he's trying to find the mass of the Earth. But so what he does is he compares them because he knows the force of gravity between these two balls. And he knows the force of gravity between the Earth and the small ball. That's just the weight of the ball, right? And if he can compare them with a proportionality statement, boom, bada boom, bada bing.
What does that have to do with the Earth, though?
You get the mass of the Earth.
No, but does he set up this the Earth as one ball?
No.
What does
there's a steel. So there again, this setup is still the same way.
Okay.
The smaller ball, he knows the force of gravity between the small ball and the Earth. That's just the weight of the ball. He also now just calculated the force of gravity between the small ball and this massive ball. So by comparing the masses and by comparing the forces of gravities, he deduced the mass. Yes, there it is. I was waiting for this moment. He deduced the mass of the Earth.
That's crazy.
That is crazy.
No, that's crazy.
But what's crazy is that it's not even over yet.
What?
Because literally after he died, 75 years later, scientists recreated this experiment and were like, God damn, this guy missed a crazy crucial part, calculating G.
Yeah.
Right?
The proportionality.
Exactly. Again, by the way, so G is the F equals GMM over R squared, the gravitational constant from Newtonian gravity, which was because remember when Newton invented this equation, G was just a proportionality constant. It wasn't a number that they knew. They knew the units for it because obviously they knew what it had to equate to, but it wasn't actually a number that they had any idea about because they just wanted to understand the relationship between these variables. They didn't really care about the values. But then, Henry Cavendish comes up and says, well, I want to actually know the value. So anyways, I mean, he didn't, again, do the G part. He did the mass of the Earth through which he calculated the density of the Earth. And he was like 1% close to the actual value. So he was crazy good. But
which is still like the actual value isn't the actual value.
Again, yeah, it's
because
still like
it's still an
it still has it.
experiment.
It still does. It still does.
Yeah.
And this is also in like early 1700s.
Yeah, so it's like current value.
1700. So it's insane. But again, the 75 years later, they recreated this experiment. Literally, there's no mention of G in the whole paper, in whole Henry Cavendish's experiment about this paper. No goal that was not even a part of it. But an interesting thing about knowing the mass of the Earth is you can calculate small g, like the gravitational acceleration. Now, a thing about the gravitational acceleration is it's also related to the gravitational constant. And through that, there's basically a relationship of the gravitational constant to this whole experimental setup. And they found G basically using that. So
that's a fun experiment.
That was
that's
Cavendish's experiment.
That's crazy.